Thanks to generous support from EMC SAS, Schwab Performance Technologies, the ePartners Program, and the NC State Engineering Foundation. And in this first talk in the academic year in the series, we have Dr. Radhika Kulkarni with SAS, who will be telling us about how we can succeed with business analytics, about the key challenges and solutions. Dr. Kulkarni is Vice President of Advanced Analytics Research and Development at SAS, and she oversees software development and analytics solutions. Welcome, Dr. Kulkarni.
Thank you, Radha. Thank you so much for inviting me, and good morning to all of you. And I'm honored to be here. It's always a pleasure for me to come to a university campus and speak with students and faculty members because it's really wonderful. So I'm very happy to be here. And I hope I can give a little bit of insight into the analytical challenges with big data or small data. You know, just because everybody's talking about big data, it doesn't mean that we've solved all the issues and problems with small data either. So there's a lot of wonderful, interesting problems which are at the intersection of knowing a lot about computer architecture, computer science, and analytical methods, algorithms, and methodology. So there's a lot of intersection there, and the more we dive deep into it, the more we find that, oh, we need to find out so much more about how we can solve some problems. So hopefully I'll be able to give you a little bit of an insight on where we are with, and how we address some problems. So my talk today, I'll address a few things. I'll talk about what is business analytics, what do I mean by business analytics, what does SAS mean, and what does the world mean by business analytics, and what are some of the key challenges in today's marketplace, and how it gives us some opportunities for innovation. And as well, I will talk about some of the big barriers to success. So I'll cover a lot of this using some examples which illustrate how things work together, okay, and where the types of different analytics come into play. So I'll start first with a couple of examples that all of us can relate to, because that, I think, is a good way for us to see that almost in everyday instances of interaction with businesses, with each other, there are many analytical problems being solved on the back end that you may not be aware of. This particular credit card fraud example I like to use because it's something that all of us are familiar with. You know, how many of you have had the unhappy circumstance that you've gone to pay for some sale and your credit card gets rejected? So it's probably happened to many of us. And if you're in a foreign country and you don't know, oh my God, I don't have cash, I don't have this, it's really a big problem. So if you think about all the things that goes on behind it, there are models that are being built. So for a bank, of course, if there's a fraudulent charge, and especially if the charge is a pretty large amount, it's a big loss for them. For the customer, of course, it's a big pain in the neck, and they get very irritated with the bank. Why did you stop the card, and so on. But of course, if I'm the card holder and somebody has stolen my card and they're using it, of course, I'm very thankful that the bank is going through all this, right? So what happens? So what happens actually is that every bank or every credit card company, they have all these models that they build, which takes into account different attributes, which might be things like geography or the location. So if it's actually a shady neighborhood, they're probably, and you're charging something, they're probably doing a lot more, you know, the probability of it being fraudulent is higher. So they use all these attributes as to, normally Radhika does all her shopping in North Carolina. Suddenly I find that there's a charge in Germany, there's another charge in Finland. Is it really a real charge that she is making? Those are the types of questions that come up. So having been through one such place where you get stopped at a payment, what do? The next time you call a credit card company and tell them I'm going to be in Germany, Finland, so you know that they won't charge it. But suddenly if the charge appears in some other, in India, for instance, they might say, oh, what's going on? So these are all the types of things where models are built using analytics, predictive models, which says, okay, if the price is this, if the charge is this, and if the location is this, then the probability that it's fraudulent is very low. Otherwise, in some other cases, it's high. So those are the types of checks and balances that they use before they stop the payment or accept the payment. And all of this happens in an instantaneous second. So the model building, which gives you the equation which says whether such a charge is fraudulent or not, actually happens offline. But the scoring, which is what happens as soon as a card is swiped, all the different attributes are fed into the scoring engine, and then they tell you yes or no. Okay, so that's exactly what's happening. So usually it's some kind of propensity for being a fraud and so on and so forth, which is quite deeply analytical, the models that get built. So you can see the need for speed in this, right? Another thing that is also affects all of us, and we've probably seen instances of it, when you go to any grocery store or some of the department stores, quite often your receipt on the back end has some offers that it gives you. And those, again, they're using some analytics in the back end, which says that this type of purchase or market basket, these are the types of things that have been purchased. So this person is probably likely to buy more peanut butter next time they come around, so coupon for peanut butter, et cetera, et cetera. But again, some models are built offline. This particular company is Catalina Marketing, and they are probably the most often used company which produces these coupons at the back of receipt. And so this, again, are models that are built offline, but then you need the ability to score them. When I say score a model, what I mean by that is just think about a regression equation. Y equals alpha x plus beta, alpha plus beta, x1, et cetera. If you take that as a regression equation, calculating the alphas and the betas are what you call by building the model, determining what the alphas and betas are. But then once a particular event happens, you know the x's for that particular event. Fill all of that in. The y is what gives you what is called scoring the model. So data miners use the term training for building the model, scoring for actually finding out what the value of the y is for a particular instance. So it's the scoring that needs to take place very, very rapidly, because you need that to happen instantaneously most often. So these are the types of problems which pose some computational challenges, and I'll talk about that when I get to the computer architecture and so on. Okay? So I hope that's given you an idea of some types of problems that we need to solve and the types of challenges that you might have there. Okay? So first, let me set the baseline in terms of what I mean by analytics or analytical methods and algorithms. It's anything related to statistics, data mining, forecasting, optimization, text analytics, and you name it. So there is a word cloud up here which gives you all the different expertise areas that are classified into what one means by analytics. And usually, when you say advanced analytics, it's mostly some algorithms that that are quite deeply theoretical, that you need to be able to learn quite a bit about how to develop those algorithms and then put it into practice and so on. So these are all the different subject areas which are coming into play for solving some business problems. So business analytics is just the application of advanced analytics, which includes statistical models, forecasting, data mining, optimization, all of them to come together to solve some critical business decisions based on either operational data or customer data or a combination of both. So the two examples that I gave, there's a lot of information about the demographics of the person who's swiping the card or who's buying the list of items at the grocery store. There's also some data about the geography of the place. All of that go into building the model, but then the transactional data gives you the instantaneous decision. So business analytics often is a combination of building the right model and applying it for specific decisions. Okay? So what I'm going to talk about for the next, the rest of the time is talk about some current trends in analytics which are driving innovation at different levels. Before I get to that, let me talk just tell you a little bit about my division, because that will give you an idea of the types of people who are working in my division and how they collaborate, because I think one aspect that I'm very proud of and very passionate about is fostering that collaboration. So I've been at SAS for 31 years, and my division consists of mostly PhDs, some master's students in statistics, forecasting, econometrics, optimization, and so on, and they all contribute to what is known as the SAS analytics portfolio. So that could be the SAS Stat, SAS OR, SAS Enterprise Miner, and so on and so forth. And for the past many years, there's a lot of collaboration that goes on, because no one particular problem is restricted to a particular domain. So we interact and integrate and collaborate in many different ways. And I think all the new challenges that are coming up are actually making this interaction and integration and collaboration that much more important. Okay? So what are some of the trends that we're seeing? Of course, big data, right? You hear about big data as a challenge everywhere. And the question sometimes comes up, is it a lot of hype? Or is there some really value that you can gain from using all the data that's available? And there are different problems for which just a sample of the data is good enough. In other cases, you need to look at the entire data that's available. So this slide just gives you an idea of the explosion of data. So, I don't need to dwell too much on that, but it's mind-boggling how what used to be considered big data, now nobody considers it as big data because it's become just exploded in other dimensions. But what are the types of data that come into play? That's also a challenge. And if you look at some of the sources of big data, age, height, weight, price of sale, quantity of sale, those are all attributes that we've always had. Statistics, which SAS especially, it's very relevant standing on the NC State campus because SAS was born on this campus, and it started with analysis of agricultural data, which was basically crop yield and what was the different characteristics and they were all analyzing fairly big data sets at that point in time, and all of it was numbers and either ordinal or nominal characteristics. They were all structured data. So now we have a lot of information that comes to us in the form of text. All the Twitter feeds, the Facebook blogs, everything. There's a lot of textual data. There's a lot of video images, voice data. All of this contributes to the explosion of data. So not only do we need to know how to analyze all the different structured numbers and other information, but we also need to know how to incorporate some of these other types of data. So this is where really the explosion comes up. Can you imagine how many copies of the picture that you just took at some party get posted and whose Facebook account and everywhere? That's all floating around somewhere. So just imagine how this explodes. So so big data is here, for sure. In some cases, I thought it would be useful to take a couple of examples and talk about how using big data, using all the data, you can really get some very useful insights. And this is an example that a colleague of mine pointed to me, and I think it is a very, very interesting example. What you're seeing here is an artist's representation of a gene, and what it's referring to is tamoxifen. It's a drug named tamoxifen. How many of you have heard about its success in breast cancer? And some of an early analysis of data of who was given tamoxifen, who recovered from it, they realized that it was effective in 80% of a particular type of breast cancer. In 80% of the patients that were given tamoxifen, it was effective and they were cured. So, but having access to all the different drug trials, all the different cases where it was administered, they did a lot more analysis of looking at the genetic makeup of the people who were getting the drug. And a very wonderful insight came out. And that was that 80% of the population have a particular genetic makeup. For them, this drug is 100% effective. For the remaining 20%, it's not going to work. So what first was telling us, the insight we first had was that it's effective 80%, and that's usually done with usual statistical analysis. You can get that kind of inference. But looking at the entire use cases and entire history that they had, they were able to actually narrow it down to saying that for a particular genetic makeup, you know that it's going to work 100% of the time, and 80% of the population have that. And so imagine that is a huge insight, because you need to just check whether, okay, are you a person for whom it's effective or not, and you don't go trying to give a drug that's not going to make any sense. And so this is a very wonderful story, which in fact, I heard something about this even on NPR. So it's a very nice illustration of where using all the data gives you better insight. Okay? A couple of other examples. United Healthcare is a particular, it's particularly valuable to think about this. Looking at voice files from customer calls to call centers, they're able to get a lot more information. So this is one example where using information about calls that come into your call center, they can get a better insight as to the quality of care that was provided. And they're looking at providers and how effective they are and so on. So this is one example where taking voice data or data that's been collected, take that into text, and then incorporate it into your analysis gives them a lot more insight. I was at a presentation at a Disney Analytics conference, and the speaker there talked about how at one of the major clinics, I believe it was the Cleveland Clinic, the electronic medical records, where there's a lot of physicians' notes, nurses' notes, if they can take all of that information, take that text data, and convert it into additional information that they can categorize, looking at all the call notes, all the notes that they've collected, that gives them even better insight at a diagnosis, in addition to just their flu and their temperature and their pulse and BP and just everything else they say. So taking all of that, how do you get more insight? That's a very, very good example of how text data augments even day-to-day things that you might run into. Okay? GE. This particular one, this big data in big companies, there is a reference at the bottom. There is a book or an article which talks about lots of these examples, and that's a very, very illustrative article. So I would encourage you to take a look at that. So I just picked a couple of examples from there. So sensor data. We're going to see a lot more examples of where sensor data comes into play, and using the sensor data to predict when something is going to break. So for GE, for instance, when they're looking at turbines or aircraft engines, being able to look, you can imagine the price of that, how valuable or how expensive those huge big parts are. Now, what they are trying to do is to make sure that they catch a potential failure that's going to happen much before it happens. So more and more sensors are added to the different aspects of this, of any of these instruments, of this equipment, and collecting all of that data and putting it all together, and then being able to analyze and looking at a predictive asset maintenance is the term used quite often for this area of analytics. What do you do to look at all the data that's coming in and collecting it? So this is one place where the explosion of data is huge. Nowadays, even in cars, I believe at Ford Fusion, I think that's the name of the model, they're capturing everything that's happening with the car. You know, how fast you brake, how you accelerate, all the different ways in which you turn. So every minute they're collecting tons and tons of data. So if you take all of that information and put it into some location, insurance companies, if they had access to it, they'll know right away, okay, this person is a dangerous driver. So they might, so there is some danger like that too, right? Too much information about you gets public, and you may never get a license to drive if you're a bad driver. But you know, on the positive side, what GE, so you can see 500 gigabytes per day per turbine. That's a huge amount of data. So typically, when you look at quality control, and you probably heard about how quality control played a big role in manufacturing for maintaining quality of the parts that get manufactured, the goods that get manufactured. So there's a lot of research that happened 30, 40, 50 years ago on QC charts, quality control charts. But now, when you have these massive amounts of data, and there's multiple variables contributing to the end result of whether something is going to fail or not, this is one place where you can easily see new opportunities for research. So just having a univariate quality control chart is no longer enough. You need to have a multivariate version of it. Not just that, you need something that can tell you in almost real time. So you're continuously getting this data about the different pieces and parts of this machine. You need to be able to take all of that and get something that tells you, okay, something is about to happen, or maybe you need to pay attention. So it's much less expensive to turn off a machine before it fails, fix it, and then get it running than if it fails midstream, because then you have lost opportunities, and fixing it probably gets worse and worse, and so on. So this is a very real example where companies like GE and many of the auto manufacturers and airplane manufacturers are putting more and more sensors into it, which leads me to the next space where, okay, there are all these sensors, all this data that's being collected, so you could set up some systems to monitor it. You could have some screens which alert you and say, okay, something is going awry, something is happening. Often, you may not even be able to be fast enough to react. Often, something going wrong in one part affects something else in another part. So this is where you could have all these machines kind of talking to each other. And so this particular picture attempts to give a pictorial representation of your computer talking to your fridge, to your door, so that your coffee machine, those are all simple daily life activities. But if you look at what needs to happen, you know, a nuclear reactor or something, things are happening fast, and you don't have time for a human being to react. You need the machine to react and then take all the preventive maintenance or preventive actions that need to happen. So that's what we mean by the Internet of Things. What do we, what is it? The things are any device which is collecting some data, from the smartphone to thermostats, etc., and all the different sensors. So they expect that by the year 2020, there'll be like 150 billion devices that are online. And all this data is going somewhere on the internet and collecting. How do you connect the information coming out of it to the internet? How do you collect all of this data, and how do you analyze and take action? So the Internet of Things is going to continue to be an interesting space for research and for trying to do innovative analysis. So at SAS, we are quite excited about the opportunities it gives us, because we can take some of the methods and applications that we have for the general usage that our customers have been doing and scale it up and make it much more scalable, handle large data, etc. So the Internet of Things is giving us a new life to do fun research. Okay. So where are we on that? Again, some of it I've already mentioned. I believe it will become part of our daily life, so that I think your car might decide that, oops, this person is being very, very dangerous right now. Let's stop the car. That would be dangerous too if you stop on I-40 coming here. So there may be some alerts or something. Oh, it looks like Radhika is falling asleep. Alert and give her some boost, or just a warning message might wake me up. So those are the types of things that would affect us in our daily lives. Those are simple things, but much more complex actions will continue to happen. GE, I know one of the people who was working on this aircraft engine problem, and he said that they're investing a lot in hiring people who can analyze the data, people who can look at the problem and figure out what's needed. So it's an interesting space. So more and more companies are looking at what are the ways in which we can harness some of this. Okay, so I've talked about some business problems. I've talked about how there are opportunities and huge ways in which we can do research in this. So let me talk a little bit about how we are approaching some of these challenges and problems. So fundamentally, in every one of the problems I described, the need for speed is pretty clear, right? Your credit card, you can't wait for 5 minutes before they say yes or no. It happens instantaneously. Many of the other actions I talked about, the more quickly you can react, the better off it is. So then also being able to do big data analysis comes into play when you're trying to make specific decisions, not just on the entire population, but on different states, different counties. Each one of them might have a different type of model that needs to be built. That's what I mean by micro-segmentation, where people are making offers, putting out an offer for lots of heavy winter jackets. That's probably more relevant in Minnesota than in North Carolina. So you need a different model for Minnesota and a different model for North Carolina. You could, in some cases, you might need to go even more micro-segmenting, right? So micro-segmentation is one place. Automation across thousands of models. That's what I meant, where you need the models to run automatically and build automatically, and so on. So these are all the different problems or problem spaces where we need to be decreasing the latency at every stage. So I like this particular figure because it says, being able to decrease the latency of identifying the problem, identifying what model needs to be built, building the model, scoring the model, all of these, you want to decrease the time it takes to do that, because any delay in that is lost time, which actually translates to value. In some cases, huge value. Okay? So reducing the time to market or the time to action, reducing the time to anything is where all businesses are trying to go. So what does that mean? It means that we need to be able to handle analytical methods, produce analytical methods in all of this. And something that my division is continuously working on is how do you deal with all sizes and volumes of data. So there is that, the analytical methodology that needs to happen. Then another aspect is, where are all this data being stored? Where is all of this being stored? And there are many databases which hold data for the transactional, for data, there are data warehouses, there's historical data, transactional data, and this is a computer science audience, so you know about all these names: Greenplum, Teradata, Oracle, and Hadoop. I'm sure how many of you have heard of Hadoop? Yeah, this is great because I think most audiences, I think now actually it's interesting, even in non-technical audiences, people are raising their hands. But I expected everybody to have heard about Hadoop here. It's essentially an open source method, storage as well as computational environment. So data could be stored in these proprietary databases. They could be stored in Hadoop. And a lot of companies are now recognizing that Hadoop is a way to reduce their cost of storage. So a lot of companies are moving to a Hadoop storage. That the beauty is that you can also use Hadoop, the Hadoop servers as a computational environment as well. So some of the work that I'm now going to describe is the different ways in which we have addressed this need for speed on all these appliances or all these hardware platforms. Okay? So the computing platforms and the fact that we've got Hadoop, which is relatively inexpensive compared to Teradata or IBM hardware, is a result of this. Computing platforms are getting more and more cost effective, and being able to put a lot of commodity hardware together to create a network of computers that you can use for your computation is actually one of the places where we can take advantage of. Okay? And distributed computing, again, that's not an unknown term to this audience. You all know. We've tried to break up work and do parallel computing, grid architecture, and so on. So the journey that at SAS we have taken for high-performance analytics can be captured in this one slide. So the first thing, of course, is take all the work that you have, distribute it across your computer network, and break it up and let each computer, each node, work on different pieces of the problem and bring it all together. That's what we refer to as the grid computing, the first column. And on the left, that column just basically says you can have SAS running on each one of the hardware, and I say SAS, but it could be R, it could be any other software package as well. You have installed version of the software package on every one of those nodes, and there is often some utility routines which can help you distribute your work so that each computer, each node is working on an independent problem. And then, of course, sometimes it might have to wait for everything to finish. Sometimes it can continue. So that's a paradigm that's very commonly known. Okay? So, and we've got a lot of success with our grid computing software because people really are able to get a lot of value from that. One of the disadvantages, one of the drawbacks, is that if you've got your data stored in Teradata or Greenplum or any one of the databases, in order to run SAS on those data, what you really end up having to do is to move the data to your computers, or it might be groups, parts of the data to your different computers, and that often is an expensive proposition. And so, so people end up taking samples of data or paying the price of moving the data. Okay. I remember, I told you that there are two aspects of solving a business problem. One is training the data or finding the alphas and the betas, and the other one is actually scoring the data. So often what people do, what businesses do, is train the data or build a model on a sample of the data, and that happens offline. So you can pay the price of the time it takes to load the data into your computer network, build the model, and then use that model, the alphas and the betas, to, I've simplified it by saying alphas and betas. Sometimes the models are much more complex than just an equation. When you build a neural network model or a decision tree model, you can't just represent it as an equation. But the notion still carries forward, right? So usually you build the data offline, and then you're scoring in real time or near real time on every customer. So if you're building a model which says, what is the probability that someone is going to have a positive response to an offer that I make him, you calculate the model, and then you're looking at all the customers that you want to run a campaign on, potential customers rather, and you're scoring all of them and saying, okay, these folks are more likely to respond than those folks, so I'm better off campaigning to them than to the rest. So that's what I mean. So that needs to happen on a much larger population, or typically your entire customer base for bank offer where they're trying to make additional offers. Or if you're trying to acquire new customers, you might send it to everybody, figure out who in North Carolina you want to target. So that is typically needs to run on a much larger data set. So SAS in database was the next path or next step in that journey. We said, okay, let's assume that we built the models, but you want to run the models and score everybody who's in your database, and those could be a Teradata database, IBM database, et cetera, et cetera. So these are all the places where the transactional data or the customer data and their information is living. So can we do something there where you're just running the scores in there and not having to move all of them into your computers to do the scoring? And that also is a very successful effort where you're not necessarily doing all the complex modeling on the data, but you're actually running the scores. And if it's represented as an equation or some data step code, you can run it. And in database computing is actually something that's very, very valuable to a customer to be able to use. The Catalina marketing, where the point of sale data that I talked to you about, that particular example was the case where the models were built offline, but then the scoring was done in database. And so that was our next step of the journey. Then, of course, once you start doing that, the next question is, can you do something even better? Can you build your models closer to the data so that you don't have to move the data? So the SAS in-memory analytics is our next step of it. And I think that actually is where a lot of work has been going on across SAS to how to build the architecture so that you can take advantage of some computing resources that are available in the same nodes where the data are living. So that's important. So let's take a Teradata appliance or Hadoop. Every one of those, it's at the end of the day, there is storage, there is also some CPUs there. So the question then comes, can you not use those CPUs to do those computations? The in-database computation actually also happens inside it, but it's actually using the same process, the same place where the data are stored. And usually because you've got transactional data and an operational system, you don't want to run algorithms that could bring it down or slow it down. So running it in exactly the same space is usually frowned upon. So in this particular, the way of handling this is in-memory analytics. What we do, think about all these nodes where the data are residing. So can you just use a separate process in each of the nodes to do your CPUs, to do your calculations? And can you move the data within each node? But now, of course, for a big data problem, you may not be able to put all the data on a particular node. The data are distributed. So sometimes you might need to take your algorithm, which needs to run on all the data, and break it up in a fashion, reinvent the way, so that you can do some computations on each of it, then come back and do some aggregation, go back again. So do a more iterative type of approach where you're splitting up the work and doing it in a clever fashion, so where the work is not embarrassingly parallel, where it's all completely independent, but it's actually interrelated, So there the challenge is you want to minimize the chatter between the nodes. Okay, so I gave you all this preamble to run this. There's a little bit of an animation here, so watch what happens. So the idea that I just described is shown in this. So the gray disks are where the data are. The place where you've got the SAS logo is the same nodes, has some piece of SAS computational engine installed in each one of those. Not necessarily the entire SAS system, but just the algorithmic, the math symbols. So when you see when you see what's happening, you'll see the client is where on you're sitting at your computer, you send proc HP reg or something like that over, and did you get that? Okay, when I was explaining. So the message goes across. It says that, okay, I need to do some computations. It takes the relevant data from the disk, moves it within the node. So that's a much faster data movement than taking it out. So in the traditional way, you would have to take all of the data out to your computer, to the client place that you're sitting at, but it's moving it just to within the node. The computations happen. So there were some orange balls that ran across, which was all the computations on each node, and then there were some blue balls running across. That's the internode chatter. So how do you minimize the internode chatter and try to change your algorithm? So this is where we've spent a lot of effort over the past couple of years, actually for the past 3 or 4 years. So what I want to, and it was incredible. The excitement in our corridors when we first did this was just wonderful, because the first example that they tried was for some risk computations, then for some logistic regression, and this particular one, it gives some before and after type of numbers, where in the current process, a neural network, to run one iteration of a neural network method, in the high-performance process, we ran 100 iterations of it. It took 5 hours to process one iteration when you did not use the computational distributed computing hardware. To run 100 iterations, it took just 6 minutes to process the model. And we've got much more incredible numbers as well, but this just gives you an idea that by being able to... So what's the advantage of this? When we first started talking about this, we said, okay, we've got a logistic regression now with high-performance computing. We can get the logistic regression to run in a few seconds, where it would have taken you several hours sometimes if it were billions of records. What's the big deal? Anybody who builds any of these models knows that in order to get the best model, you have to do a lot of experimentation with different settings, different parameters. So I'm saying that because you might wonder, why did you get an increase in the performance as well? I mean, not the speed performance, but in the performance of the model. So you got a model lift of 1.6% in the first case. It went up to 3.2. That's because running 100 iterations of a neural network model gives you a chance to get a best fit, much better, a better fit rather. Okay? So, and of course, the speed or the quality of fit also is affected by how many different types of things you could run. You could run logistic, neural, decision trees, all of that. If it's going to take a long time, you're limited, of course. But if it can run very fast, you can experiment. So this is where the value of the speed up comes in. Okay? So this, in this screenshot, it's a screenshot of our enterprise miner client. And at the back end, lots of models run, lots of algorithms, neural networks, decision trees, all of these run in the back end. And we spent the past couple of years or more working on high performance enabling all of these methods. This is just a small list of it. So we did this for data mining, we did it for optimization, many of the statistical models, and so on. And it's been a really exciting time for everybody. And there are lots of opportunities for collaboration between the optimization people and the data mining people, because now you can start using some of the optimization solvers in a much more distributed fashion to get a better neural network, support vector machines, and so on. And that can be a separate talk all by itself. Okay, so I won't go into that. So So I talked about the business problem, some of the ways in which we can help customers solve them. So is this the end of it? Is it enough to find ways of solving these problems, of solving the analytical challenges, of storage challenges, or is there more to it? And my claim is that that's just a small piece of it. You know, solving the problem mathematically is exciting, it's innovative, you can get a result. The place where we really have challenges, when we go talk to customers and tell them, okay, we've got this wonderful way of solving these high-performance problems and so on, there are other problems that come into play, and I'll use a few examples to do that, to talk about it. First of all, do you have the right data? Because, yeah, you can, you know, your temptation would be to throw the algorithms at all the data that you have. Do you have the right data? And that challenge remains, whether it's small data problems or big data problems. So, and there are many examples we can talk about, but this one I thought is a good one to think about. So having the ability to solve some of these challenges opens up the horizon to incorporate other kinds of data that you might not have thought about. So this one, particularly, we call it the social network and analytics, but essentially what it means, so if you're trying to make an offer for a smartphone, let's say, and you know, iPhone 6 came out, and before that, if Apple were to send out coupons or whatever offers to different people, it could take a look at all the information about individual people and their attributes and decide on the basis of that, okay, these are the folks that would be most likely to buy the phone. In addition, now with all the social media information that you have, look at the Facebook friends, look at their LinkedIn connections and say, okay, you know, Radhika has only 10 Facebook friends. Well, I don't have 0 because I don't have a Facebook account. But somebody else, my son, is an iPhone fanatic, so Apple fanatic. So he definitely would wax all eloquent about it. So of course, giving him an offer is probably much more valuable than giving me the offer because he's going to talk to all his friends. But then there might be somebody else who has many more friends than my son, so maybe I should give it to him rather than to my son. So this is where all the connectivity comes into play. But for that, you need not only the attribute information of individuals, you also need to know the connections, the networks. So can you capture that network connections, the network data, and how do you use that? And this particular paradigm is useful not just in this marketing sense, but also fraud detection and terrorists. So knowing who is talking to whom, knowing that there is one bad guy somewhere, and oh, okay, who are the people he's talking to? You know, probably he's the bad guy too, and so on. So these are all the different applications. So including network information is another kind of data. I talked to you about including text information. That's a different kind of data. This particular one is an interesting one where if you're trying to do revenue management and say what kind of prices should I set for hotels, it of course helps to know how are people choosing it. So when you're capturing that information, you have the information that I picked, king-size bed, non-smoking, etc. But you have that, you don't really know what were all the choices that were given me. Maybe there was nothing else, so I picked it. So there's no way to conclude that I like king size with non-smoking. Maybe I would have liked the suite. So you don't know. So this particular case, when you're trying to do revenue management in an effective way, you need to now think about, okay, now that I have the ability to do some choice modeling, I need to be capturing some data, not just about what they selected, but what were the choices. So that's another example of do you have the right data or not? Do you have the right process? There's lots of operational challenges. How many of you have been to Disney World recently with a magic band, right? I meant to bring my magic band, but I forgot. It's like a Fitbit, but it actually captures your room key information, your park ticket information, and everything that you've told them about yourself, so that you are your fast passes, which rides do you want, and so on and so forth. So this was a huge project for Disney to put into place. So getting the magic bands was one aspect, but now they have to put sensors in place to know where you've gone. So they do, or they can tell how long you waited in the It's a Small World or Space Mountain, that you waited 40 minutes, 55 minutes, and probably after 3 rides where you waited an hour each, they know that he's probably not a happy camper today, so they might offer you something. So these are the types of ways in which they want to use. So the types of problems that they could solve are easy to think up, but then the processes that they have to put in place, the sensors, that's huge. So it required a big change in infrastructure for them. Markdown optimization. You can figure out how to mark down the prices every day. You can change the prices that you put on your clearance items, but somebody has to go in and tag them, or you need to find a different way automatically of doing that. So this is, again, a change in process. When you're trying to make offers to customers, again, you could have different campaigns. You have campaign managers. This basically is, what offer do you make to which person at what time? So that's generally what is known as marketing optimization, where there is a customer population, there are different offers you want to make, and different channels. But the challenge here is, in any retail bank, for instance, there are different campaign managers who are responsible for different pieces of the population. Now, if you put them all into one big marketing optimization engine and solve it, okay, you've got the solution, but it might so turn out that Radha has got no campaigns this year. She cannot make any offers, whereas Radhika has been given 100 offers she can make. Now you need all of us to sit down and explain why that's good for the company and what is the incentive so that you are willing to give up your offers to somebody else. So it's a mind process. How do you think about it? So these are all some of the challenges that are much harder to solve, much harder to implement in a company than actually doing the analysis. So I just wanted to give you an idea of that. Do you have the right talent? Do you have the people who can execute to it? So some ways in which we help that is hiding the analytics behind some simple user interface, educating them, and training them. So we call this the democratization of analytics, where at a call center, you call up a telephone company and say that, oh, I've had a problem with my phone. Then they might say, okay, I'll give you, they solve your problem, but then they give you an offer. Radhika calls India very often, so let's give her an offer for calling India. But the person on the switchboard is not really knowing, he or she doesn't know what analysis to run. It's all hidden behind it. So that's what I mean by democratization of analytics. That's one way to address some of that. UPS instituted a huge system called Orion, where it was actually optimizing the way the packages are delivered, the drivers, what route they should follow, etc. This is, again, a good case study that's in this article. So for them, they went through the analysis, figured out what needs to be done, but they invested a huge amount of time and money on training the drivers, training everybody who was going to touch it. So, but for all of this to happen, the person right at the top needs to believe that this is important and invest in that. Okay? So there's a very nice article about that. So these are some of the benefits, and I'll leave this slide deck with you so you can see some of the ways in which they were able to reduce a lot of expenses because of this. Okay? Then educating, of course. How do you educate them? And this is where, universities, what are the types of problems they should be looking at? What are the types of disciplines? How do you make people think about these? And giving them real experience and to try out these different methods. That's a big, big push that we need to look at. So for each one of us, businesses, educators, students, what are the ways in which we can learn about some of the challenges? What are the opportunities? And how do we exploit them? And this is a question that all of us need to be asking each other. How can we do all of that? So I think, I've covered a lot of ground. I hope it was useful. So,
thank you very much. You talked about social network analysis, but do you consider augmented interaction can be emails and chat messages, and that is like a privacy of concern.
Yes.
How do you plan to address that?
Yeah, there are lots of privacy concerns. It's almost like Big Brother is watching you, right? So I think, we think our email is private, but somebody has access to all of that. Those are, they border on the ethics and the organization and the legal concerns as well. And especially in the era of big data, it's not just even the emails and stuff. You have so much information stored about different people that any level of anonymization may not really protect your anonymity. Because if you know everything about a person, the age, the characteristic, and where they shop and all of that, they might be able to, even without the name, they know that it's Radhika who did all of that. So, and there's a lot of research about that, and the answer is still not a very clear one. How do you protect anonymity? But the specific one that you asked would be more bordering on, okay, what do organizations, what are they allowed to do? What can they do with that? And how they go forward. So it borders more on trying to look at some organizational behavior and so on.
On the video part, the SAS, you mentioned that pieces of SAS are loaded. Is that sort of every time? In other words, do you say you have to load clock reg on there every time, or are they permanently resident pieces of SAS that the controller?
Yeah. So so when you get the HPA proc, HPA, high performance analytical version, in the distributed version of it, they're actually, like if you were licensed for the statistical module, then a high performance, each one of those would already be there. So all the HP stat modules, regression, reg, and logistic, neural, they would all be there. In there. So, and they're much smaller than the entire SAS system because it's just the computational piece. Yeah.
So you mentioned G in one of your slides. One thing about there are some data that don't come in a clean way. You can think of sensor data. So what's your take about data pre-processing integration to make
that's a very good question, because I agree, that's an aspect that I did not cover in this, but data cleansing, data quality is a huge aspect. Before you even start using analysis, that's a huge aspect of it.
Are there tools from SAS to automate?
Yes, we have a data quality product that helps you with that. So.
I have a question that's also what he asked, what Anup asked about privacy, especially important in the Internet of Things. Do you need really raw data from end users? Can there be an alternate model where you can build some sort of small models at the end user level, and what you get from them is the models, and you compose or you take these personalized models and generate data, which doesn't necessarily match what the end user has. Can privacy problem be on the data cleaning?
Perhaps. We've also talked about data generation, generating data to build some of these models. But that's, again, a different research topic, right? So how do you generate data that captures the attributes and characteristics? So it's some kind of simulation, data simulation. How do you simulate data to capture that?
I would say that you need to completely simulate. You can, end user can train a model, and then they share the model instead of sharing the data.
Exactly. Yeah, when I say simulate, it's based on some.
So a lot of these predictive analytics and stuff that you're doing, a big problem with doing that kind of prediction stuff is false positives, right?
Yes.
Do you guys, have you experienced, are your models, you're talking about using neural networks, do you guys have a method of dealing with those false positives, or is it that you've trained the model so much that they're small enough, or how do you mitigate that?
So in most of the predictive modeling stuff, we have the training and validation. So it's extremely important to make sure that you have a good set of validation data. And, whether you do, and I think the enterprise miner paradigm allows you to set aside data for that and test data. So, and the best way to do that, of course, is generate it, try it, and do model comparisons. So.
Okay, so you guys just try to keep the false positive rate as low as possible. But is that a problem? Because, even, if you get a false positive rate of something like a 10th of a percent, if you're running that over, 10 million people and saying that's still a ton of false positives. That could be reports, or you're offering somebody that they're like, hey, a new car. And,
Yes.
I'm never going to use that.
And Professor Dickey might have a more statistical way of answering that question. The best way, most modelers, what they do is by evaluating a bunch of it and comparing on their test data, on their validation data, which one has better, what would you call it? Better metrics. You have a lot of metrics that you evaluate and look at it and say, okay, let's look at all these metrics, and is there one particular model that actually does better than that? There's no way of preventing that as well, but it's more by comparison. So you need to have a model comparison ability for anything you do. So it's, are you better than before? Are you better than everybody else?
Sure.
Thank you.
I wonder if you can comment on sort of your view of how the U.S. is doing in building kind of capacity for analytics, and particularly relative to Europe and Asia. I was just chatting with a colleague about natural language in particular, and there seems to be a much stronger infrastructure, research infrastructure in Europe. So I'm really curious.
Yes, there is a stronger research infrastructure probably in certain areas. If I look at the entire population of what people need to learn about analytics and all of that, if you look at, not the research level, but more a broad base, being able to address analytical problems, which is where the base of the analytical talent needs lie. I do think U.S. does very well because we've got a lot of good programs which train people to address that. If you look at research areas, it depends on the area. I wouldn't be able to comment on the natural language processing area, but if you look at statistics, optimization, and forecasting econometrics, we have excellent research going on in all of these topics. So NLP might be a little bit different. I'm not sure you know more than I do. I'm able to comment on that, but I find that there's a lot of exciting research going on here.
One question. You showed you had three models. The foremost one is being the in-memory analytics. What about streams?
So yes, that's and I think being able to solve something, the fact that we're able to solve some of these in much higher, more performant. At least we're addressing the algorithmic part of it. But how do we deal with streaming? So we have an engine called Event Stream Processing Engine, which actually allows you to capture data and continuously get the data. So you're getting data, and there is we acquired a company to do that. And so there's the ESP engine, which is actually getting data from these sensors, and we are doing a lot of research and figuring out. So we know the technology, we know what to do with it. We're trying to figure out which are the killer applications that we can apply. But yes, being able to solve them properly, quickly as they come along, and you may not be able to store any of the data, so you need to be able to address a moving window of data that we have, and how do you keep updating. So once again, dealing with streaming data for scoring is a much easier problem than for building the model. So how often do you need to retrain it? How often?
More questions? Let me just mention that Dr. Kulkarni has graciously agreed to stay around until around noon. And so specifically, if you're a student and you would like to talk with her, and
Yeah.
she's still open to this.
Yes.
Okay. Let's thank her again.